Hello, everyone. My name is Vikram Monga. I work for VMware based out of Los Angeles, California. Today's topic is unwrapping the layers of software-defined networking traffic flow. Software-defined networking has introduced a distributed network architecture into the data center, where every node in the fabric participates in network and security functions. This limits the number of network bottlenecks in the network or environment, but it also creates a new challenge for understanding network traffic flow. In a traditional network architecture, there are specific switching and routing devices through which traffic must flow. But in the distributed model with the software-defined networking, east-west traffic flow can function on all hypervisors in the environment. This can make traffic monitoring and packet captures more challenging. Since there is not a single isolated point in the data center that is most critical, we should qualify that by saying that for north-south traffic or traffic leaving the data center, it is necessary to pass through an edge gateway or a collection of ECMP edge gateways. So north-south traffic has definite points of ingress and egress, but our focus here will be on east-west traffic within the data center.
Even though all hypervisors can deliver networking and security functions, there are still particular points in the hypervisor where we can capture traffic as it flows from and to workloads. Now, you may say that this is not security related. Packet captures are mostly concerned with network traffic path and flow, but software-defined networking with NSX challenges those distinct boundaries between networking and security. With NSX, network objects like logical segments can be used as security zones, for instance. Firewall rules can also be built around network segments. And from a security threat perspective, lateral movement in the data center or within a single network is a very common strategy to gain greater access to more critical workloads and data. NSX is designed to preclude this type of lateral attack. And at the end of the day, without network traffic, security is not needed. Security is dependent on traffic flow, and understanding the traffic path is essential for constructing a robust security posture. Networking and security, as essential functions of any data center, are interwoven and intertwined, composing the fabric of the modern data center. In this slide, we can see the different packet capture points at different stages of traffic flow. When capturing egress traffic at the VNIC of the VM, we will use the VNIC TX function in conjunction with the switch port ID associated with the VM's network. We will show how to locate these requirements and how to build out the packet capture in the demo. As you can see, there is also the option to view traffic pre and post DV filter. This parameter will allow us to see traffic prior to and after hitting the distributed firewall. Thus, traffic that is blocked by the DFW will be visible pre-DV filter, but will not be present post-DV filter. The next capture point will be on the uplink associated with the switch port in question. So for egress traffic, we can use the port output function to view traffic prior to encapsulation. Then the uplink send kernel function will show the same traffic after encapsulation, where we will see the TEP IP addresses at the head of the packet.
Starting at the host VNIC for ingress traffic, we'll use the uplink receive kernel function to view the encapsulated packets as they are received on the uplink. From there, the packet is decapsulated, that is, the TEP IPs are removed, and then we can see post-decapsulation using the EtherSwitch dispatch parameter. Finally, for ingress traffic, we use VNIC-RX function with the switch port ID again to see traffic being sent to the destination workload. You have the same options of pre and post DV filter to see how the DFW affects the traffic in question.
So onto the demo. We'll be working with our Gryffindor application and here. So we've got Gryffindor Web, Gryffindor App, Gryffindor DB that make up the Gryffindor application, and we can verify that functions as expected at the moment, and it does. So there we've generated traffic here. Now what we'll do is we're going to take a look for the first part at a packet capture between two VMs on different hosts. So we'll start with Gryffindor Web. This will be our source VM. and you can see that it's located here on ESX01A. And we'll also take a look at our destination VM, which is ESX02A. Of course, these are two different hosts, and this would be a common traffic flow for this application, since the web server communicates with the app server over port 8443. So the first thing we'll do is get a PuTTY session to both ESX01A and ESX02A. So on the left, I've got 01A, and on the right here, we've got ESX02. So ESX1 has the web, Gryffindor web. ESX2 has Gryffindor app. So one of the ways that we can, the first thing that we need to do, and the first capture point that we're going to see is going to be starting at the source. So that's going to start at Gryffindor web, since traffic is going to start from there, and then the destination in this case is going to be Gryffindor app, since web initiates the connection to the app server. What we'll do is we'll run ESX top here, and you'll see all this information, but then you'll just press the character in on the keyboard, and you'll get to see all the networking information on this host and all the switch ports and Ethernet interfaces for all of the different workloads on here. You can also see the PNIC that's associated with each workload. So these are really important as we build out our packet capture. We need to know what port ID we're using here. That's the switch port ID, the one that's associated with the kernel inside the host for switching. And then of course the uplink, we'll also need to understand that as we move further along. So for Gryffindor web, right, that's the one that we're going to be working with here. We can see that we've got this switch port ID, and it's using VMNIC2. Go ahead and collect this switch port ID and just copy it to our notepad here. Press Q. And in this case, this is going to be, if you remember the slide we had, it's going to be VNIC TX is going to be the parameter that we use here, right? So this is how we'll build out the packet capture. You'll start out with PKT-CAP-UW. This is how you would start out every packet capture on an ESX host. -- switch port, and then that switch port number that we just found for Gryffindor web. And then you'll specify the capture point. So like I said, this one's going to be traffic that's originating from the web server, destined for the app server. And since we're running this on the switch port of the web server, this is going to be transferred traffic, so egress traffic. So we'll do VNIC TX for egress traffic. And we're going to filter this via IP. And I'm going to filter it by the IP of Gryffindor app, which is 10.0.1.12, as you can see here. That way we get more specific detail on capturing at this point, because the web server could be communicating with other devices and is communicating with other devices, including the originator of the connection to the web server. And then we'll do -O dash, and this just simply keeps this parameter here, just ensures that the packet capture output is going to stay within the console. You can specify a certain file to send the capture output to, and we'll do that later on as well. But for now, we'll just keep it in the console so you can see what I'm talking about. That's the TCP dump feature here. So this is what the capture should look like to see egress traffic from Gryffindor web VM here. So we'll go ahead and press enter. Can't see anything right now, but we'll generate some traffic and see if we can find what we're looking for. Just refresh the page, and there you can see got some action. And here 10.0.1.11, that's our web server. And you can see that it's communicating to the app server, which is 10.0.1.12. exactly what we filtered on in the packet capture over port 8443, just as we would expect for a web to app connection. So we can see that the traffic is being sent from Gryffindor Web to Gryffindor app in this case. Now, this is prior to being sent out the uplink interface, right? So this is just being sent out the VNIC of the VM, and that's what we're verifying here. So and you know, right now we're not worried about DFW. We know that this flow is already allowed. We verified that previously. We will cover a DFW use case here in a moment, but primarily I just wanted to show egress traffic from a VM and what that would look like. So now that we've verified that, we need to check to make sure that this traffic is getting to the uplink of the source host, which in this case is ESX01A. And we want to check that before encapsulation and then after encapsulation. So doing it, as you can recall, our uplink is going to be VMNIC2, as we saw from the output before. So I'll specify uplink instead of switchport here, and uplink will be VMNIC2. Capture point this time is going to be port output. So this will be prior to encapsulation, if you recall from the slide we showed earlier. And we're still going to filter by this IP address. Reason being is that we should still see this IP address and be able to filter on it prior to encapsulation. After encapsulation, we'll have to filter through a different parameter, the VNI of the logical switch. So let's see if the traffic is getting to the uplink from the switch port of the VM. And yep, there we can see. So we are getting traffic from 10.0.1.11, our web VM, to 1.12 over port 8443. So we verified that traffic flow is getting to the uplink from the switch port. So next thing we want to do is check after encapsulation, and to make sure that we are, before this packet leaves the host, that it's getting to the uplink. So basically this is right as it's egressing the host and going out to the physical, we can verify that last point of capture. So one of the things, like I said, we're going to have to change up the filter here. You won't be able to filter on this IP address since it's going to be encapsulated, and we're going to be using the TEP IP addresses and so forth. So instead of that, what we'll do is we're going to filter on the VNI that Gryffindor is using. So if you take a look at the segments here, Gryffindor LS is what we're using for this network. All of them are associated with Gryffindor LS, both Gryffindor Web and Gryffindor App. So we can locate that VNI on the host here by typing in NSX CLI and then get logical dash switches. And here you can see that Gryffindor LS has this VNI of 67590. So just something to note here. And we'll use that as our filter. So you can exit out of the NSX CLI, return back to the root of the ESXi host, and we can build out our next packet capture to verify that traffic is leaving the source host encapsulated as expected. So pkt cap-uw. This will be on uplink vmnic2. And this time the capture point is going to be uplink send kernel, since this is of course egress traffic. And then we'll change the filter to VNI, and then that's 67590 is our VNI. Show dash TCP dump dash UW dash ENR space dash and leave that open. And you can see the packet capture is working, but we don't have any traffic yet. So let's generate some. And there you can see, I'm just hitting Control C to exit out of the capture there. And so what we can see here is that, and this is the reason why we couldn't filter on 10.0.1.12, is that the packet's being encapsulated. And now we have 192.168.130.42 as the source, and 130.41 as the main destination, since these are the TEP IP addresses on the host. But you can still see that we can see the original packet here listed just later on and protected within that encapsulation here. So at this on the uplink send kernel for a logical switch or logical segment, you're going to see two sets of IP addresses and two sets of MAC addresses, one for the TEPs and one for the internal workloads. And so this is exactly what we do expect to see here. So we verified that all the traffic is successfully leaving the VM. It's getting to the uplink of the host, and then it's leaving the source host destined for other host on this network, ESX02A. So at this point, we want to check to make sure that the destination host is receiving this traffic. So since this is going to be ingress traffic, we're going to work from the reverse side. So we'll start at the uplink and work our way to the destination VM. So we'll do the same thing that we did last time. And we'll do ESX top, press N just to see. And you can see that Gryffindor app here is using VMNIC2 as the uplink. And of course, here is the switch port ID. So I'll go ahead and put the switch port ID again in my notepad here. And we'll put this as destination switch port ID to specify. Okay, so now I can start building my packet capture again. So PKT or PKTCAP-UW uplink VMNIC2 again, because we see that here. The Gryffindor app is using that, and that's our destination workload. And going back to the packet capture, what we're going to be doing this time is the uplink receive kernel, right? So that's going to be our parameter, our function here, our capture function. And again, we'll filter on VNI because, of course, this is still encapsulated traffic that's being received here. This is prior to the decapsulation that must occur. And we'll capture the traffic after the decapsulation, but you can't filter on the workload IP. You'll have to filter on the VNI. And it's going to be the same VNI, 67590. That's going to be consistent across the fabric. Okay, packet capture is written successfully. You can see that it's working. Let's generate some traffic. And there, you can see it. So again, we can see that it's coming from 192.168.130.42, destined for 130.41. These again are our TEP IP addresses. So the 130.41 is the TEP IP address for this host here, ESX02, since this is, the destination host. And of course, 130.42 is the TEP IP for ESX01, the source host. And again, we can see inside that, we've got our original packet here over port 8443. Okay, so now we've verified that the physical fabric is successfully delivering this traffic from the source host to the destination host. The control plane is working in that, the VTEPs, we have the correct VTEPs in place. So this is looking really good. This is an expected traffic flow. So now let's see if we can see what this looks like after traffic is decapsulated. So again, we're gonna use the uplink here because decapsulation occurs on the uplink, but we're going to change the capture point. And this time it's going to be capture on ether switch dispatch. or disk path. And we can go back to filtering on our IP address. We don't have to filter on the VNI anymore. So 10.0.1. We could do .11 since that's our source, or we could do .12 like we were doing prior. Let's see if that works. And yep, we don't get an error here, and it's staying open. So that means our syntax is correct for the packet capture. Let's generate some traffic again. And there we can see it. Okay, so we actually see a little bit more here. This is the database server actually that we're viewing here, but this is our packet from web to app. Again, this time it's not this is post decapsulation. So again, we don't see the TEP IP address, we just see the workload IP addresses. So we can we verified that encapsulation is working from the other host, and on the destination host that decapsulation is working. So now what we'll do is we'll move back to the switch port ID and verify that traffic is being delivered to the VM as expected. So this will be, ingress traffic. So we're going to use the VNIC RX or receive function. So again, we're going to go back to this switch port ID that we located when we use the ESX top command on the ESXi host. And we'll change the parameter from uplink to switch port again, put in the switch port ID. Capture point will change this time to VNIC RX again. We'll filter on the IP address of 10.0.1, and this time we'll filter on the web IP address since that's the one we're concerned about. That's 10.0.1.11 TCP dump -UW -ENR space dash. Hit enter, generate some more traffic, and bam, there you can see we've got traffic is being delivered successfully from the web server to the app server. So we just followed that packet from source to destination at all the different points on the fabric, from switch port to uplink prior to encapsulation, to uplink after encapsulation, to the destination uplink, to the destination uplink post decapsulation, all the way to the destination workload itself. Now, of course, you can combine these at the same time and perform these packet captures at the same time if you'd like. And but that's the first part here that we wanted to show you. All right, so next, now that we've verified and we followed a packet from source through the host switching connection and modules, all the way through the uplink to our destination host, destination uplink, and our destination workload. The next thing I want to show you is the options that you can, more specifically with security, and how you can view traffic prior to the DFW being hit and then after the DFW being hit. Now, of course, in this case, the previous case that we were looking at, the traffic between the web and the app server over port 8443 is an allowed traffic flow. So we would expect that if we were to look at the filtering there, we would absolutely see traffic prior to the filter and post the filter. And the VNIC VNIC RX function there is definitely post filter. So, but let's take a look at a flow that is not allowed, right? And see and show the differences between pre-DV filter, which is where our DFW is, and post-DV filter. So now that we have shown the packet flow from a source VM to a destination VM, following the host switching all the way to the source uplink, seeing encapsulation, and then seeing it being delivered to the destination uplink, seeing the packet post decapsulation, and then finally being delivered to the destination workload. Let's involve a security use case more particularly, and that's the DFW. Now, in the packet that we just looked at and the flow that we just looked at, Gryffindor web to Gryffindor app over port 8443, that's of course an allowed flow, right? So the DFW is not blocking that. So we would, if we did do a packet capture on the DV filter, we would see that flow present both pre-DV filter and post-DV filter. But now what I want to do is take a look at a flow that is not allowed, so we can see that traffic is being successfully blocked by the DFW. So we'll start here on ESX01A, and instead of getting the switch port ID, we are going to get the slot 2 filter, which is where the DFW runs on the DV filter. So part of that process, we're going to just type in the command summarize-dv filter, and you'll locate Gryffindor Web 01 is the one that we're going to work with. Of course, you can grep for this if you need to. We can see it here. So here's Gryffindor Web. Again, you can see the port ID. But what we're concerned about, since we're going to perform this packet capture on the DV filter, is we want the slot 2 filter, the nickname. So this is the one we're going to capture. So let's save this to our notepad that we have going on there, our host here. The flow that we're going to take a look at is actually from this particular machine, which is DNS server, and has an IP address of 192.168.110.10, right? And we're going to try to SSH to the Gryffindor web server, and that is not an allowed flow. So we'll see what that looks like, right? In this case, it's going to be, this is going to be ingress traffic, right? Since the flow is coming from the 192 address and going to the Gryffindor web. So pkt-cap-uw. Again, we'll use the capture function, and then the parameter that we'll use is pre-DV filter, just like that. And then --DV filter. And then we'll capture that name that we have here that we just copied. Copy that out again. And we'll filter again by the IP address of the source. So it would be 192.168.110.10. And again, we can just show you that here, that this is the IP address that we're working with. -o-pipe TCP dump -uw -enr space dash. All right, so that looks good. Let's go ahead and hit enter. Okay, and again, this is pre-DV filter. So this is before the DFW is applied. So let's see if attempt SSH to this workload. So we'll just hit putty, new session, Gryffindor web is here. And you can see that it's not, the SSH session is not establishing, right? But we can still see the packets. So we can see that 192.168.110 to 10.01.11, destination port 22, as we'd expect for SSH. We could see that pre-DV filter. So now let's try the same thing again, but this time change the capture filter or capture parameter to post DV filter, using the same filter ID that we have here, using the same IP function, since we're going to be doing the same workflow again. And this time we'll hit enter, and we'll attempt to connect to Gryffindor web over SSH again. And again, you can see that it's not connecting. And post DV filter, we're not seeing the traffic. That means, so we saw the traffic pre DV filter here. When we changed it to post DV filter, we don't see the traffic, and the connection is never successfully established. Therefore, we can see that this traffic is being blocked by the DFW in the DV filter of the VM. Now, in some cases, you might want to do some offline analysis, and you may not want to put all of this stuff in the console. There may be too much content. You may not be able to filter it out enough to view everything in the console. So, I want to show you what it looks like to save a packet capture file on the ESXi host, and to review that and take a look at that in a Wireshark application. So we're going to still work with the same VM though. And again, we're going to type in ESX top and hit N again, just to go back. And of course, you can see that Gryffindor web has this switch port ID. So one of the neat things about the VNIC TX and VNIC RX is that you can run both of those at the same time. And so I'll show you that here in just a moment. So what we're going to do is we're going to save a packet capture file to the host. And you want to make sure that it's a one that you can download from vCenter, so a location where you can download from vCenter. So in this case, we'll go to CD, VMS, VMFS, volumes, LS. Let's take a look at what we have, and we're going to save it here because I can save the file here, download it from vCenter client onto my own machine, and then upload it into Wireshark. So that's what we're going to do. And just do a PWD here so you have the path. And now we can start creating our packet capture. So PKT, CAP, -UW again, switch ports, and oops, missed a hyphen there. Switch port. We've got our switch port ID for Gryffindor Web is here. It's also up here just in case. So 657, 657, yep. And capture VNIC TX, and then comma, no space, VNIC RX. Okay, so again, this VNIC TX, comma, VNIC RX means that I'm capturing both ingress, or I should say egress first, and then ingress traffic. So we're capturing both directions on this switch port. So any traffic that's coming into this VM is what this is going to capture, right? All right, so, and then instead of using the TCP dump feature that we used before, we're just going to remove that pipe and TCP dump. We're going to say -O, and then you're going to specify the location and your file name. So again, we did the PWD to get the path. So that's going to be our path there. And then we'll create a file name for our packet capture. So I'll say Gryffindor-web.pcap. You want it to be a .pcap file so that you can upload it into Wireshark and view its contents. So we'll go ahead and press enter here, and let's generate some traffic. So we're actually capturing something. And once you're seeing traffic, you should see the number of packets that's being collected, showing in the console here. And then just press Control-C to exit out of it and stop the capture there. And if we hit LS, we should be able to see, yep, we can see that our Gryffindor Web PCAP file is located in this local directory on the ESXi host. So now if I go into vCenter, go to storage here, and go to local ESXi, take a look at the files, and wow, here I can see the Gryffindor Web PCAP file that I just created and collected information from. So I'll go ahead and download this so that it downloads to my own personal machine, put it in this volume here, and then we'll locate our Wireshark app, open that up, and we'll do file, open, locate our packet capture file here on the eVolume, and click open. And now we can see everything that we captured in that file here in Wireshark, and we can really get specific in how we filter out and view some really interesting stuff about the packets. But in this case, you can see that this is actually what starts the connection, right? So again, I'm using 192.168.110.10 as sort of the control center for this lab, and that's where I'm actually initiating the traffic to the web server, which is 10.0.1.11, and that's over port 443, as you can see here. So here you can see the Ethernet information, destination MAC and source MAC and so forth. And of course, here you can see the IPv4 information, and it's really specific. Okay, so we can see that connection is being established successfully. And so now if we continue going down here, we should be able to see here. Yep, here we can see that within less than a tenth of a second, we've already started communicating with our app server here. So you can see 10.01.11, the web server's communicating with the app server here over port 8443. And then that is being established and the flow is continuing. So we've looked at three different things here. We've examined a flow from two workloads on two different ESXi hosts and the different capture points that you can see to verify that traffic is being passed along the correct path. We've then taken a look at the DFW parameter, pre-DV filter, post-DV filter, to verify that traffic is being blocked successfully or being processed successfully through the DV filter in whatever way that is. And now we've taken a look where we viewed offline analysis and collected a file from the host and uploaded it into Wireshark to get more detailed look at the traffic that we're passing here. So that's it for this demo. Thank you.